Gentlemen, we're about to start. I'm asking for silence. We have a Netflix in the room, and we're going to be recording our Netflix special today. Just kidding. I'm just trying to keep you awake because I know that it was a hard day, a long day, and I really appreciate everyone who stopped by and decided to join us today. I was telling to, like, every time I travel to places, I really, really love meetups, even though my purpose of being here is a JFocus conference, but I really love meetups because this is where actually dedicated people who are interested in subject or in the speaker will be there. So that's why I'm telling you thank you for stopping by. My name is Viktor Gamov. How many of you actually came from the Kafka user group to this? Okay, we have one person. The rest of this is a Kong user group. Okay. All right, this is great. So in this case, it's my favorite crowd because how many of you are using Kafka, or at least like reading something about this, or interested because like fear of missing out of this? Okay. So after this presentation, you will have a pretty good understanding on the technical level and also on the practical level how you can use Kafka, and if you are even developing APIs, you're developing applications, how Kafka can be integrated. It's another way of communicating things. How many of you heard this story about the elephant and let's put this for some old men? So whenever they were old, they were blind, but they were very wise because they've seen things during their life. And for the first time, they met elephant. When they met elephant, each of them will try to touch different part of this weird creature. Someone would touch the nose, someone would touch the legs, tail, and based on whatever they have experienced in life before and what they feel like familiar, some say, oh, it may be snake because the ponytail, or maybe it's a bigger Burmese python when they're touching the nose. So. Okay, Victor, why are you telling us this? Because this is exactly answering the question, what is Kafka? Because it really matters who you're asking. Kafka becomes for the last, I guess, 12 years, almost 13 years, as a technology that becoming a backbone of IT infrastructure, data infrastructure. And even after these years, and I've been doing this for quite a while, like talking to people about Kafka, talking to people about explaining what it is. We still have people who are not like fully understand or like what is this? Is it like messaging, or it has a key value? Can we query this? Is it like a database, or like is it somehow to relate it to Spark because there's Kafka streams and there's Spark streaming? We know this. So really depends who you're talking to. And today I will explain kind of like a vanilla story behind of Kafka. And my name is Viktor Gamov. I work as a principal developer advocate at a company called Confluent, and I'm Hobbit. You will ask like, what? Yes, because it's like in a Hobbit, there and back again. So I've been in Confluent, I went to work for Kong, and now I'm back at the Confluent right now. So I've been in both positions with the API development, with application development, stream processing, data integrations, all these things. And yeah, I love to hang out with people like you because this is giving me some of the ideas what the people building, or maybe I give them ideas what to build. So, quick agenda for today. I will introduce you to event-driven architecture as API developers, application developers. You're probably familiar with the concept of REST, request response, WebSockets, all these type of things. But how it fits in the event-driven architecture. And I explain all the basics that you need to know about Kafka. We will talk a little bit about async API, but previous presentation covered a lot of aspects already. And yeah, let's jump right in. So instead of telling you, doing blah, 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 I decided to show you. Let me show you something that is event-driven application. I don't know if it's visible, but I do have a map of the city of Stockholm. And we will have two applications, ride-sharing application. I'm traveling. I don't know the phone of taxi, but I'm blessed that we have something like Uber or Bolt where I can just get the app and call the car. So same app we'll have here. And I'm staying somewhere in a hotel that someone needs to pick up me from this venue and drive me to my hotel. So I'm here not far from a train station somewhere here. So I want to put like my position here. And nothing happens because I am dumb. I will put my position one more time. And now I appeared here on the driver radar. So driver knows that he needs to go and pick me up. So in this case, driver clicks, and we establish that's not supposed to happen. Let's do it one more time because again, you always need to refresh things before before you start clicking around. Okay, let's do here. It should appear somewhere on the driver side, and it didn't. So also good thing because we can restart and start over. So that's the perfect segue to some of the infrastructural side of things that we're going to be covering in a second. But you know, a few people saw in the audience, they saw this before and they know that it actually works. So yeah, there's some people who can vouch for me. Okay, and I'm just do docker compose down. Just killing everything, start it over. Up, docker compose up. Oh, 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 oh. So we have a writer application. We do have a driver application. And now, hopefully, everything will work out. We have driver, and we have somewhere here will be our writer. So I want to go here. Now, the driver sees this, and driver can say, yeah, okay, I'm going to go and pick up this one. And now I also start receiving this notification, so I would know how far is this car. So it is quite, probably many of you done something like this before. Technologies like REST and WebSockets basically drive this application. But these two applications, even though they're running right now as a demo on my computer, they actually don't know anything about each other. They are only focused on their own thing, what they need to do. So first of all, my driver application would be listening topic with the writer requests, and we will come back to this because it's everything is happening in real time. It's also pretty cool. Each this service will have a color coded because this functionality will be depend either we're consuming this data or we're producing this data, and the Kafka will be in the middle. You probably realize that we use Kafka here somehow. So application, like a driver service, needs to read information about writers. So that will be consuming writer topics, but also it needs to advertise itself. It needs to send information about the driver position when the writer picked up. So driver service will produce the messages inside this topic. And when we have a writer service, we need to do vice versa. We need to find the available drivers and produce information about this. So on the technical side of things, here's your better UI that you were asking. If you ever installed Visual Studio Code, you can go install Confluent extension. And now you can connect to any Kafka cluster. And as you can see here, I do have two topics, that information about the driver, and information flows through this topic. And I can see, inspect individual message, and see what are positions of this driver. So it's on the low level. And on the high level, this is two front-end talking to each other through WebSockets, but they're not talking to each other directly. They're talking through a Kafka topic because these two applications will have producer and consumer. And this is very important because this is something that you need to, as a developer for those type of systems, you will find yourself in a situation where your application will and produce and consume on the same time, and you need to find the ways how you either will be processing this information or whatnot. And this is the pattern that event-driven application will use. You will listening. You're not actively asking. You're not requesting this information, comparing to REST, right? And you just do your thing whenever the message will be triggered. So, and see in a few seconds it will reach, and everything will be cool. Does it make any sense? Can I explain this any simpler? But by this time you already start. You should start, and it's when there's the silence in the room. There's two things. It's everything is clear or nothing is clear, and since there's silence in the room, for me it's also difficult to figure out if it's everything is clear or nothing is clear. Everything is clear or nothing is clear. Yeah, you know stuff, like, you sit down, yeah. We know each other, like, he's one of Confluent community catalysts, the people who work with Kafka and Kafka community. And yeah, he wrote a bunch of Scala code, and we still can be friends, even though I usually try not to shake hands for people who write Scala code. Anyone writing Scala code for money? Okay, good. Anyone writing Kotlin code for money? What kind of languages folks were using here? Java, okay. Golang, it's fine. Yes, totally fine. Python, C#, it's perfect. Why Java developers wear glasses, right? Because they cannot C#. Anyhow, so we're going into world of Kafka. So I already throw a bunch of ideas. I throw the idea about the topic, some messages, like a consumption, production. So let's talk about this. Let's talk about how it works. So Apache Kafka, it is an open source project that was initially developed at LinkedIn to solve certain problems that they have, specifically speeding up some of the ingestion time for some of their like Hadoop application. And that time when the Kafka was designed and the ideas about this, how it could be cornerstone or like a central piece of modern data architecture, it was not there yet. Now, today, Kafka used and power multiple different use cases. Use cases that will require data integration. Kafka ships with the connector framework that virtually connect any data source to any data source. You can easily replicate data from MongoDB to Postgres and vice versa using Kafka connectors. Kafka, it is a distributed transactional log. So in some sense, it's also database because it provides some level of persistency for the messages that will be stored. They are not ephemeral, like in your messaging system. When the message is consumed, it's gone. In Kafka, they are durable. They stay on the disk. So that allows to implement interesting use cases. You can reply this Kafka log and reply all these messages as much as you want, because you might have a different use case. For one use case, for same amount of data, you're just interested in simple filtering or transformation. For another use case, you will be interested in something like that will be more complex, that will require enrichment and maybe join with some external sources. So everything is possible to do right now in Kafka. Also, I apologize for this because I already developed the professional information. So every use case that you will throw at me, I can solve this with Kafka one other way around. Even though sometimes it might feel as over-engineering, but we not call it over-engineering, we call it building for future, right? So in future, we might need this, yeah? And when the people are saying that about different use cases, or we're too small to use Kafka, or we're too big to use Kafka, in this type of conversation. So, yeah. Now, in the center of Kafka is the concept of topic, and the concept of topic is not very interesting because topic is just a logical thing. But more interesting concept of Kafka partitions. So inside, if you ever seen log file, how many of you seen log file before? Just a simple text log file. What do we see there?
Lines.
Lines, perfect. How we reading log file. If we're interested to get some history, we reading line by line from top to bottom. No, kind of from top to bottom, from beginning to the end. Another thing is that a log is something that we use as a data structure that allows us to understand what happened. And as long as we don't have any like malicious ideas, we're never going to change log records, because this is our source of truth that we can restore from this kind of like a set of events. But in order for you to get the full picture, what happened with the system, if there was a failure, or maybe we start losing some requests and things like that, we need to somehow read all this log file and get story out of it, right? One way or another, based on some of the technical knowledge about the system, and we can put some meaning in what we're reading. Same thing, the same idea was taken and implemented as a data structure that Kafka would be using, and this is how Kafka became known for. Distributed event log, every message that will be written from append to the end of file. Each individual messages are immutable. Everything you will not be able to change once it's there in Kafka. There's certain technical ways how you can remove the data, but technically, if you have an infinite log, you're not removing anything from it. Inside individual message, we will have some interesting parts. Specifically, Kafka really doesn't care what you will put there. Kafka knows it bytes, and those bytes will be stored in there, and some additional information also will be serialized and stored inside the Kafka message as a byte. Additional information, like a header. Messaging people would be excited about the headers, because in the past, headers was used to provide some additional metadata, maybe how this message needs to be routed, or maybe like origin, or some additional things, like when the people try to build some of the synchronous communication, like RPC-based systems. Anyone who built RPC-based systems on top of Rabbit, Kafka, or something like that? It's a safe space here. We can talk about this stuff. It's not a crime. But it's something that extremely difficult to do, because you need to find the ways how you can correlate request response. Because the example with this taxi driver and taxi rider, they're using different topics to communicate, and only my application logic sitting somewhere there knows how to correlate this event. So if its event came from this particular client ID, we need to send this to particular WebSocket. So I know how to correlate this. So header is very useful in Kafka as well. So some of the frameworks, like Spring Boot, for example, in Java, a very long time if you're using default serializer, it will put class information inside the header. It's very useful when you kind of like using this Kafka as a communication medium between two microservices written in Spring Boot, because they use the same serialization, deserialization logic. And now we have a key and value. And this is also a very interesting concept that sometimes throw people off in terms of like, okay, so it's a log, we're writing something, some event, but key value. If it's key value, we know the key, we can query this, right? Not entirely true. So key, in this particular case, used is the way how we can route those messages. And let me explain you how it's done. And topic is just the combination of different partitions. You can have multiple partitions per one topic. You can have one partition per topic, and that's totally fine. And inside, say, transactions topic, messages that will come in from single producer will be strictly ordered inside partition. Not inside the topic, but inside this partition. I will show some pictures in a few seconds that explains like how it works. But if you want to visualize yourself, and we'll never forget, I have two analogies, one with chess, one with banking. And I found that people pay attention about money more than they paying attention about the chess. So that's why always like a credit card transaction type of use case always works. So say if you want to have a system that can capture all transactions that happen for one particular credit card in order how these transactions were executed, you will be using a partition key equals our credit card number. So based on this credit card number, all transactions will land in one partition. But if you have a different credit card number, so all these transactions will land into another partition. So that's very important to understand in order to understand how the Kafka does things like consumption and processing and aggregation and something like that. And two components that will be responsible to, we're talking to Kafka, they are low level. There's some frameworks that already implement certain things like stream processing for Kafka, it's Kafka streams, or Flink. For Golang, there's Gosu, I think. There's a few frameworks that do this. In Python, there is Robin Hood library, it's called Faust. On the C# side of things, I don't remember if there's actual implementation of the streams, but the C# client for Kafka is also great. So I don't know, I asked the LLM like how I can show producers kind of, stacking messages in order. And it's like, hey, you have producers that, standing in order. I don't know what's going on here. So Kafka producers are it's API. It's the client. It's something that your application will be doing. And we already talked a little bit about the messaging key. It's what we call consistent hashing or client-side routing, where your client and your broker, they already agree about the schema of exchanging these keys. So clients knows where that will end, and the producer and consumers will both know how to consume message for a particular message key. Very important piece of functionality that arrived in Kafka a couple years ago, together with some of the transactions, for example. It's called idempotent producer. In distributed systems, network is notoriously difficult to do because there's something related to physics, something related to the cables and stuff. Sometimes it's DNS, sometimes it's DNS. With distributed system, network is always something that will bring things down. Kafka clients and Kafka broker, they designed to be work in environments where the failures are inevitable. And this is how we need to mentally approach any type of distributed system that we're trying to build. Only thing what you can do is to find the ways how you can reduce the blast radius for particular failure. In the way how, say, producer solves some of the problems when there's a flaky connection between broker and producer, very simple, some client-side buffering, and after that retries, and all these type of things. In the past, when the idempotent producer was not available, with these retries, Kafka can register certain messages like more than once. And that was causing some of the problems because people who write the application, they didn't expect the duplicates would be in Kafka topic, and all of a sudden, because of this very fuzzy acknowledgement schema that's happened between producer and the broker, things got not super nice. People got frustrated and things like that. So idempotent producer guarantees that even because of the network failures in some of the kind of like lights flickering thing, the message will only appear once if it was produced once. If your application intentionally sends two duplicate messages twice, there's nothing we can do. We don't look into actual payload. But some of the technical problems solved with idempotent producer. You will understand a little bit along the way why it is important, because this is a cornerstone of the concept of exactly one processing, which is another very notorious problem to solve in distributed systems. And they kind of like, it's also technicality. In order to increase, someone asked about questions about throughput, how certain, operations that happens between the conc gateway and say from the conc gateway, from the plugin into Kafka. So those things can be optimized by configuring the size, how long the producer can hold some of the messages before they actually send. So you can define a size of batches in terms of number of messages or size. Also you can apply the client-side compression. So Kafka supports compression. It can store a compressed payload, and only when we need to do something with this data, we can decompress. So it can save some of the bandwidth and storage as well. As we established earlier, writing messages in producer until the end of the log. And if we don't have a key, Kafka used this round-robin approach where the message without key will be randomly written to Kafka partition. But if we have a key, this is what I was talking about, consistent hashing that happened between client application and the partitions. So the key would be hashed, and after that, we will take number of partition, and we'll get the number where this particular message will land. So this is how we implement the ordering in the partitions. Now, my favorite slide. Hopefully after this presentation, you will never gonna forget the concept, very important concept that I wanna talk about is what we see on the screen right now. Birds. Okay, what kind of birds? I mean, like not the type because I have no idea because it's also AI generated, but they're so cute. So three things actually we here. Not only birds. What you see, but I see different things, and I will explain this in a second. Mommy bird, right? It's kind of like a big one, or maybe daddy. I don't know. Baby birds, and nest. This is what normal people see. But after this presentation, this is what you will be seeing. So, very important concept in Kafka. Many people already aware that Kafka has capabilities for being super fast system for data retrieval, and the consumer group idea and the consumers was one of the architectural decisions that help to establish Kafka as a standard when you need to have like a one writer, many readers. Kafka is super fast on the reads, and essentially there's a couple components involved in this. When you're consuming your messages from Kafka partitions or Kafka topics, you're consuming these using consumer client application. And like, for example, if there would be only one baby bird, and mommy bird will bring, say, 5 tasty wormies, so only one consumer, only one baby bird will consume all the 5 the partitions or tasty wormies. And for many applications, it might be okay. You have just one consumer, you'll get all the data. But at some point, you decide, okay, so what about I would like to scale my reads. I want to read faster this data because I need to process this faster. So we have another baby bird hatched. And so what the mommy bird will do, it will stop them to consuming. So saying, hey, no. And evenly distributed this tasty wormies between 2. Now we have number 1 will get 3 because we are taking only things that another baby bird will require. So we'll take 3 partitions to this baby bird and 2 partitions to this baby bird. Now you kind of like scale double. Your consumption speed increased. And the way how it is actually configured and the way how it actually works since they join same consumer group. What's the consumer group? It would be ID that you need to provide before starting your application. So this baby bird will join consumer group, and this will signal to consumer group coordinator or mommy bird about this the new arrivals. Question to you, let's see how you would understood what I just said. So we still have this situation with 5 tasty wormies, also known as the partitions. And now, on the picture, we have 5 baby birds. But let's see somewhere here, there's another egg, and it just hatched. And we have another 6th baby bird. What's going to happen? What do you think? Anyone? Based on the things that I just described. Like a guess, like throw me something. Let's...
It will rebalance, and again, if it can allocate only 5 consumers.
Okay.
Because 5 partitions are there.
What's going to happen with the 6th baby bird?
One will be just do nothing.
He will starving, and maybe potentially die. It also happens, right? So it happens, your application started, there's nothing to do, and after timeout, this application will be died. Depends on your architecture. That's precisely right. So you cannot have more consumers, technically you can, but in practice, you need to have a same number or less consumers in the consumer group Then you have a number of partitions. So that's why it's choosing, when you're creating topic, choosing the number of partitions is also very important, because you need to understand in future what kind of use cases you might have. And if you have like a 40 partition, it doesn't mean you need to have a 40 consumers. It means that you have potentially ability to parallel up to 40 individual applications or individual services that will be consuming per partition. Okay? Now, another one. What's going to happen if baby bird will fall out of nest or leave consumer group because of the disconnection?
One of the others gets two.
Exactly. So baby bird, mommy bird will take over, rebalance everything, and now we will have one will have one. One will have two, and two, 3, and 4, they will have just one particular partition. So consumer group coordinator, it is a component. It's a process that runs inside the broker. And the rest of the stuff, your consumer, so for example, this baby bird and this baby bird, they don't need to know about the existence of each other, because there's someone on top who will decide what kind of partitions they will be consuming. The only thing that they need to specify is this consumer group ID. And this is what in distributed systems, what we call the shared nothing architecture, because they don't need to know each other. There don't need to be any kind of like metadata exchange. There is no replication, so there will be no conflicts. That's actually brilliant. Another very important aspect that I didn't mention is that since it's the kind of sequential thingy, we still need to have a way how we can register where we are in terms of reading things. And in Kafka, it's done through a thing called offset. Think about this offset as a bookmark, exactly. Somehow I forgot the word. There's a thing called, do you know what's the dog ears? It's when you don't have a bookmark, you actually like doing this with the page. That it's called dog ear. For some reason, I was like dog ear, but no. What am I trying to say? I'm trying to say bookmark. So this is the book, potentially Franz Kafka book, and this book, for example, have three. This book has three bookmarks. That will define three types of applications that will reading the same data. They will be, this is the source of truth. Kafka is your source of truth now. Everything is there, and you can go back and forth. You can reset those offsets. You can reset those bookmarks and start from whatever you like. Three use cases, three friends. One of them is me. I'm dumb. I'm going through the book and looking for the pictures. Because why not? And this is what I like to call is, not I, but like everyone, it's called stateless stream processing. Because there's no need for me to know what's gonna happen on the previous previous step, because I just like register picture in the book and hey, and after that going next picture, hey, going next. So this is, I can do, say, transformation, filtering, and maybe like throw some other message to another topic saying that, oh yeah, I registered this picture, do whatever with this picture after. Very simple use case. You all probably done something like this with any type of you doing filtering of collection or something like that. Now, we have Robin here. He's a little bit more sophisticated. So he wants to go for every page in this book and find count of each individual word. Hello world application in the data world, known as a word count. You take the data with text, you parse it, tokenize it, you remove something that you don't want to register as words, and after that you perform kind of like a flat, it's called a flat map operation that will throw new stream of words. Whenever you see one word, you will register event. You see another word, you will register one event. You see another word, you will register one event. And at the end, you will perform kind of like a folding operation. So you count this. You take all these words that will have a hello 1, hello 1, hello 1. When you do fold, you will get hello 3. So this is how you do a word count. And this is what the Robin does. So for Robin, it is important to have some sort of storage to remember what was before, because we want to do aggregation. So Robin will perform stateful stream processing. We need to have some sort of state. We need to store intermediate results. As a programmer, if you ever write application, you can use a hash map or something like that to store this individual result. Hash map may be not going to survive application restarts. You need to have something something more persistent. So that's why some of the stream processing frameworks that you will be seeing out of the wild, you need to check if it's like stateful stream processing frameworks and what kind of storage they provide to do the stateful operation. And for example, this esteemed gentleman, Tim, he might have absolutely different use case. So he's so nerdy that he takes the thesaurus, and for each word that he sees in the original book, he found the replacement. And on this on the output, he wants to have some sort of extended version where a user can click particular book and they will have alternative words for one particular word. So it is what we called stream to table join, because he might have some of the data available stored in some other data. We have a stream of events that happen that come in from Kafka topic, and on the stream processor side of things, we do join, also known as an enrichment or stream to table join, all things like that. So, and everything, all these three use cases implemented on top of the same data that already stored here, somewhere already registered. And the cool thing is that they're not going to stop when they reach the end of this file. They will be sitting there and waiting until the new data will arrive and will continue doing the thing. So I will like stop at the end of the book and wait. There will be new pages and new pictures will be printed. Robin will be waiting until new pages will be there to do count, and so far and so on. I hope it makes sense. Who doesn't understand what I just said? Again, it's a safe place. I'm here for you. My goal is to give you idea and explain things. Okay, all right. I'll trust you this time, but I will test your knowledge after. Another picture that you probably will need to have in your brain when you will be, so you get back home, you will meet your significant other, you'll have a conversation like where you've been, yeah, there was this meetup, and you start talking about the consumer groups and the baby birds and all that kind of stuff. So that's how I envision this evening will go. So when you have, in a technical implementation, have a topic with 4 partitions, and we start only one application with only one consumer group, or consumer inside the consumer group, so all the messages from all partitions will land on this application. And it would be sequential as well. Now, we want to scale this, or we want to implement different use case. So one use case is this C1, and another one, it's C2. It's 2 different consumer groups. It's Viktor and Robin. They're doing thing here. And they can scale independently. Viktor can put more computational logic. Robin can put less. Or maybe, they have because their use case will involve storage, they might need more computational logic, and the first use case might not need to. Inside this, there will be consumer processes that running inside the consumer, that will be handling individual partitions. Again, they will be handling individual partitions, and they don't talk to each other. So they don't know anything each other. So that's why there's no need to do locking. There's no need to do any type of kind of like basically lock-free mechanisms. That's we have a word from our sponsor. Like we saw a Confluent Cloud. You can try it yourself. Usually it's a $400 free credits, and you need to put your credit card. But today I have a code that you don't need to put credit card, and you still have a $400 where you can learn and play around with Kafka. Developer.confluent.io. That's the place for all the questions. So the first thing that you need to remember is the baby bird and the birds in nest. And the second thing is developer.confluent.io. So that's the website, and this is very important, developer.confluent.io. Developer.confluent.io. Okay? Like every time you feel despair, just you know where to go.
Can you zoom in a bit?
Yeah. One more time, developer, if you didn't hear the first time. So your relatives from out of town came in, or maybe they are relatives on the in-law side of things, and you don't know what to do, and you don't know how to sneak in from the house. Go to developer.confluent.io. Pretend that you learning something new and cool about Kafka. You always will be, having some good times. You learn about Kafka, stream processing. There's a bunch of free courses available, and the best way, without you installing anything, to try stuff in the cloud. So, pretty generous offer. Play around. Let me know if you couldn't find something that might be in your in the problem that you're trying to solve with Kafka. Cool. All right, any questions so far? How many of you actually heard about this exactly once processing? Some people heard, probably they saw some tweets, kind of exactly once. It's hard because exactly once, it's duplication of message, and exactly once, and message orders, and all these kind of things. I'm losing you. I'm seeing that it's getting hard. I need to wrap things up. So, many people think about exactly once the way they have their own idea what is exactly once for them. And I will explain correct way what is exactly once and how it works in Kafka. Because it's a buzzword. It's if you try to start Googling things right now, people who are building distributed systems, they will tell you that, exactly once delivery or exactly once processing is not possible because of the notoriously, or like it have these guarantees because of these notorious networks and the way how the system designed, and through CAP theorem, where the consistency, availability, and network partitioning, you need to choose only only two components that will guarantee either availability or consistency, or if you're running on a single node, you have a consistency and availability. But it's a big subject, and just simply because the way how words are matter, and this is very loaded statement. So let's talk about this. The way how you need to think about exactly once inside the Kafka, not like you have a producer, you put this data into Kafka, and you have a consumer, and everything is one exactly once kind of cycle. Who thought about this like this? Again, producer, Kafka, and consumer that needs to be executed in kind of like one exact loop. So no one from enterprises, no one from the MQ world, from distributed transactions world, no one. WebSphere people, where are you? No. It's a good country, so you avoid somehow not being there. And specifically, this particular pattern was used when you need to have, say, producer or like application that will writing data into your MQ system, and after that you need to read this and write this into database, for example. That's one of the common use cases where the message systems like IBM MQ systems, some businesses that were building these transactional management systems, they will guarantee that if a message will be produced within one transaction, it will land and it will be the transaction will be propagated down to database. And it's bad. This is super bad. This is why we have monolithic applications, because of this coupling between application code and our data store. But that time people didn't know better, so that's why this approach needs to be turned around. And the way how it exactly once implemented inside the Kafka is actually happens the vice versa. We start with consumption. We're reading data from Kafka topic. We do some processing, and after that, we're writing back results. So we're consuming, processing, and writing back results. This operation will be able to execute it in one atomic operation. Consuming data, processing. If something happens on this one, we will start over. And this is what, when we're talking about Kafka and exactly once in Kafka, this is what we mean. I'll give you an example. Say we are processing a transactions. I'm writing a application that based on the credit card transactions, or like not credit card transactions, let's do trades. Based on the trade requests that I'm receiving in my Kafka topic, I need to perform a trade. Or I need to, for this, I need to have access to my balance. So I know how much money I can I perform this operation. And if I have enough money on my bank account, I can now execute particular trade. And you can see, in this case, balance, it would be our kind of like a shared variable. And ideally, if we would design this very naive approach to solving this problem, we need to implement some sort of lock-in mechanism. So that's how databases were executing or implementing transactions. So you're saying that, okay, stop. Everyone will everyone will start here. I will execute my operation. When I'm done, I will lift my transaction boundary, the barrier, and everything will continue. So this is not like that in the Kafka world. So we're consuming data, we're performing some operations, and each individual partition will be, as we established, will be executed and performed on the particular consumer. And the processing will going to happen on this particular process of this consumer. So no one else will be able to access to this shared variable. So you don't, in this case, you don't need to worry anything about this. And why we need to have a transaction? We need to propagate transaction across multiple other topics. But Viktor, why we need to have like multiple topics? Remember this like a bookmark thingy that I was talking about, consumer offsets? So in order to application not to think about this, where to store those offsets. So me as a reader, I come to book, and the book already has my name on it. The book has my bookmark there. Same with Kafka. Your consumer group joined, and inside the Kafka, there is a special topic called consumer offsets. This consumer offsets will include information where on this log file, this particular, the consumer stopped. So that's why we're writing result back at the topic, but also we need to commit this offset saying that this operation executed in one step, so we need to advance and start consuming this message. Does it make any sense? Okay. So the boundaries between this. So first of all, producer has this idempotency, so producer cannot create duplicates. And also, producer can start a transaction. But this transaction, again, span across Kafka topics, nothing else. Now, if you want to use this and don't think about anything in terms of like how this processing will be handled, then use Kafka Streams. Kafka Streams is the built-in framework. Unfortunately, it's only for JVM libraries, the Faust, and for Python, they implementing same keeps Kafka improvement proposals, and they kind of like a very close to how it's implemented in the Kafka Streams. And in the Kafka Streams, you can just say like processing guarantee exactly once. That's it. So in the everything that will goes into Kafka Streams topology application, everything will be handled in exactly once. Now, whenever we need to, but Viktor, yes, we do have a databases, and we still need to have ability to write to Kafka and write to database. Requires additional coordination. API, in order to perform this type of communication, is available inside the framework that's called Kafka Connect. It is a special set of libraries and set of rules and tools that allow you to, say, implement generic way how we can interact with, say, any external database. There's a JDBC connector that will take the messages constantly from Kafka and execute, insert into query. So that's the example of our sync connector. And sync connector has exposure to all exactly once machinery. So technically, you with the Kafka Streams and certain connector, if it supports exactly once, you will be able to perform this in one transaction. Like the people who would be in enterprises, they would be happy, and we will hear some the people will be clapping and they're throwing things in air, so they will be super happy because this is what they like. They have a messaging system and they have a database and everything is one transaction. Need to check if it's a implementation of connect on the source side of things. If we need to kind of like someone writes transaction into the database and we need to take this all the way, I need to check the status. But in the past, it will require some additional, I guess, machinery supported on the connectors. Now, last but not least, for API developers, we already talked about the async API. And the question is, yeah, so what's this about, like streaming or APIs? So Open API specification defines how the services needs to be designed. The async API defines the way how interaction with system like messaging system like Kafka and Rabbit needs to be implemented. First of all, it's documentation and it's also contract, because some of the things that we described in the specification can be enforced by tooling along the way. And once this well documented, some other systems will not require on paper, obviously, will be easier integration. It's such a great thing to do. And I was just like putting some of the things that very similar or very different from these two specifications. So if it will take the Open API specification and Async API, they have things like operations, get, put, post, delete, and inside the Async API spec, we do have a slightly different thing. So things we call channels. We're not this specification trying to kind of a little bit abstract about the nomenclature that's available in individual system. For example, there's no topics here. So the channel will define if it's what kind of operation this is. Is it the consumption or it's the production? We have a headers, we have a payload, we have some of the documentation bit that will be, if you publish into developer portal, this information will be available there. And the message format, where you can define this in the YAML format, and it's based on this specification is nothing without actual parser. There should be something that will be turned into something useful. In this particular case, we'll take the Async API spec and generate, say, Java artifacts that will have producer-consumer code, that will have a format of the message that will be sending or receiving from Kafka, and so far and so on. Same thing is that you will take this like Open API spec and generate your artifacts for your programming language to interact with a REST service. There's a bunch of examples available. Again, we've already seen this today with Johannes showing the things. But the Async API Studio has these examples. We have people who try to use the existing parsers and they didn't work out. I've seen some of the presentation when the people were successfully using this. And I would also love to learn if people actually using. There's different approaches to how this can be approached. In one of the different approaches that we start building on streaming side of things is approach with schema registry. We starting defining the schemas because we don't care about on the streaming side of things. We really don't care about operations. Technically. Once we define the schema of the message, we can figure out how we're going to be using those messages. Either it's going to be some of the, like in my application, my rider and driver data, they look exactly the same, but it only matters when it will land on particular topic. It will include driver ID or rider ID, and it will include certain information. But from perspective of object, their description would be exactly the same. They will just have only difference between driver and rider ID. That's it. And with the schema approach, we can define how data would be. We can even restrict during if the data will not confront a particular schema. We can block production of this message into Kafka topic. it's a separate process called schema registry that will be holding information about the schemas. There's a limited number of formats that support it, but in general, like speaking to the people in industry, Avro is one of the formats that we use, protobuf. For those who like to to implement the RPC on top of, it's possible to do. Like you can implement gRPC on top of Kafka because it's already artifacts available for using the protobuf. JSON schema, and just like whatever. There's some other formats available, but they're not super like widely used in schema registry. So you have a message. I've seen some of the parsers. They also, based on the message configuration, you can actually transform it to actual schema. But every time you convert from one format to another, you need to find the ways how you correlate on certain data types and things like that. But it's possible. So let's recap. This is the last thing. Now, in the streaming world, there's the two things. There's multiple producers. There's something that will generate your data. Multiple consumers. They are not connected one to another. Like if you ever thought exactly once is what producer and after that consumer send acknowledgement that they received, it is not how we think about the event-driven systems anymore. It is message storage. In this particular case, it's Kafka. Your data is safely stored there. Kafka supports replication. Kafka supports clustering. There's different ways how you can define for replication factors. You can define in-sync replicas, how many replicas needs to acknowledge to producer. So it's like so many things. You know where to find. You know where to find it? Yeah. Where? Developer.confluent.io. Developer.confluent.io. You can find the Kafka tutorials where you can see, you can grab something, run inside the Docker container on your local machine. You can send the messages, read the messages. Kafka will provide all the storage that you need. Whereas with serverless response, you have a service, you have multiple clients that will consume it. But those things can be combined together. I showed you that Kafka can definitely provide the backbone for the services to communicate in the background. And I can go even deeper in this one because sometimes people asking, when I was at Conk, we also had a service mesh the offering that will be running even lower, and you can technically run service mesh to support Kafka networking. So Kafka would be using some DNS and all this like networking and network encryption that provided by service mesh. And API gateway can be used to implement pattern called event gateway, blah, blah, blah. So, like I said, I have a professional deformation to thinking about this as everything is a stream. I can fight on this. You can come to me with any use case, and I'm pretty sure I can build this use case using streaming. Any point, sometimes it's low engineering, but as we know, we're building for future, exactly. And the future is the data stream engineering. The future is the data stream engineering. Now, if you want to learn more about this, you know about developer.confluent.io. But, yes, of course, that's the guy. That's all you, because you give me this idea to insert the banners and advertisement inside my talk. But what I wanted to show you that we are sponsoring event that formerly known as the Kafka Summit. Now it's called Current London. It's going to happen in May. It's going to be beautiful there. If you want to learn things about Kafka, stream processing, all things data, you can join and come there as a attendee. But more interesting is to share your story. And submit your presentation and talk about how you solve streaming use case in your organization, if you brave enough to do this. So call for paper open for next 2 weeks. There's the webpage where we can go and find more information if you're in this type of jazz. With this, where's the, see, the colors are terrible. What is happening here? Why are you doing this to me? Anyway, no, but follow me on Twitter. Twitter is cool, Blue Sky is cool. Add me to LinkedIn. My name is Viktor Gamov, and as always, have a nice day. Thanks.